Hello out there. Welcome to the show. Let's get some couple of files going here and we'll let the games begin. All right, let's see. We have two sections we need to cover today. And all right, let's get some share screen going. I guess I can go ahead and log into the homework while I'm at it. I think we'll make pretty good time here today. All right, let's go back over here and get some share screen going. And all right. So let's see, I made that announcement about exam 2 and yeah, which we talked about. Actually, you probably know, I mean, I made the deadline. I extended the deadline even further than what we had agreed on in class. So that certainly couldn't have hurt anybody too much. And I haven't received a lot of any emails about it. So I guess my explanation made sense. I'm gonna go over here for a second and see. Let's see. Going to Blackboard for a second here. And I just made another announcement a few minutes ago. Not critical. Coming over here to see, okay. All right, so there it is. It's now lit up as I said it would be. So that's want to make sure I didn't make a mistake there. So technically it's open now. All right. The announcement I made today was basically giving the password for it, which was exam 2, mentioning there were 23 questions. And I don't remember, there were 3 things. I don't remember the third one. Oh, the time length was 180 minutes. So that's all. You don't need to ask me any of that today. That's all in that new announcement. Okay. All right, so let's see what we got here. Anything else anybody's concerned with before we get started here? Obviously, you got plenty of time to ask me stuff later if you need to, but all good for now. All right. So this is the normal distribution part 3, which is now on exam 3. I decided for exam 2, I just wanted to get it done quicker. So I just took off, instead of replacing the 2 problems, I just took off, there were 25. I just took off those 2 and made it 23. I could have added 2 new ones, but that's all right. It's not that big a deal. So I just got rid of those 2 that related to this topic right here. And then they're going to show up on exam 3. Now, the first 2 sections we were interested in, normal distribution. We would find a z-value or whatever, and finding the area left, right, whatever, from that z-value. Now we're going to look at this from a reverse process. If we have the area, if we know the area, can we then find the z-value that corresponds to that area? And yes, we can. If we couldn't, that would kind of end this topic pretty quickly, but we can, and we will. I call this sort of a reverse lookup process. And you're going to see how this is going to be used here in applications shortly. It's essentially for finding percentile values if the data is normally distributed. Now, we had a percentile thing we did earlier in the semester, but for discrete data. But this is how we'll do it for the normal distribution. All right. So let's see what we have here. Now let's say we're going to find a z-score that has 59.10 distribution area to its left. And so I sketched a rough picture. Now there's two ways to do this, using the chart and using the calculator. If you're using the calculator, you don't have to worry about the chart way to do it. So I kind of drew a picture. So obviously the area is going to the left, so my shading's got to go left. And I just went a little bit to the right of 0 because 0 would be 50% exactly. So I needed to include a little more than that to make it 59.1. The sketch is not that critical, but I want to make it at least look, logical. The key thing is that line I drew has to be to the right of the middle for sure. Let me bring up the normal chart here just real quick. I'm going to show you that way. It doesn't take too long to do it, but I suspect many of you aren't going to do it this way, and that's fine. I wouldn't either if I had the calculator. Well, I do, but I mean, if I was you and had this calculator. But like I said, I always like to show it because everybody may not be using it, even if everybody here attending tonight is. All right, let's see what we got here. So, before we would look up the z, we'd use that left column, we'd use the top row, and then we'd find the area. We go row, column, and then we go into whatever. This time we're doing it differently. Since we have the area, we're going inside the chart to find the number we want. So we're looking for 5910 or the closest to it. Now you're going to see this one I did on purpose to make it be exact, but some of the ones we do here later aren't going to be exact. So this time we go inside the chart to find the area right there. Then we see what row and column it came from to give us the z that we want. So you see it's on the 0.2 row, 0.03 column, so the z translates then to 0.23. As I wrote right there. And I mentioned up here, I call this the reverse chart process lookup. Instead of looking up the z to find the area, we're looking up the area to find the z. We're just like going backwards, reverse way of what I was doing before. All right, so now let me show you how to do this in the calculator real easy. Right there next to the normal CDF. Oh, my calculator might be frozen here. Sorry about that. Oh, no, okay. I hadn't used it at all today, so sometimes it freezes up. Let's see if it'll... still not doing anything. That's okay. Usually I have to just exit it out and kill it and bring it back up, and it's okay. Oh, actually, well, now it's starting to work. Oh, now it knows I tried to kill it. All right, well, okay. Wake it back up. All right, well, anyway, let me look at the next example while we're doing that. The next one says 96.16% to the right. Now, most everything we're going to be doing is in the left, to the left for this, but I want to show the right also. All right, well, no, I guess I got to wait for this. Maybe not. So 96.16 to the right is going to be a whole bunch of shading right there to the right. It's only going to, so, but to use the chart, or even to use the calculator also really, but the chart, you need to figure out what that little piece over there to the left is. And that's easy to do. All you got to do is 1 minus whatever you had there. So if it was 1 minus 9616, we'd go 0, 3, 8, 4. And that's going to be up here on the negative side. And it's right here. So it's in the negative 1.7 row, and that's the 0.07 column. So the Z value that would correspond to that would be negative 1.77. Like so. So I'm just kind of drawing the arrows using the chart. Okay, let's go to the calculator. Now, the newer calculators are a little fancier, like I've got in the box there. There's how we'll look in the 83. I'll show you what the new ones are. It's going to bring up inverse norm, and then you tell it what you have to tell it the area. So you put in 0.5910. Now notice the next one. I didn't even calculate what 1 minus that number was first. I just put it in as 1 minus that number, and that was fine. I didn't have to know that it was 0.384. The calculator obviously easily figured that out for me just by putting in 1 minus. And they made the new calculator pretty fancy here, the new operating system. Drag that. So it's the third one. Yeah, so they give you all this left, center, right stuff. On the 83, you see how it's defaulted left here? On the 83, it is left. I don't even know if you could even type in the word right and it would know anything. I don't even know. And okay, since we're using the Z's, we want mean 0 and standard deviation 1. Whenever we're doing this for regular normal distributions, we'll put we'll put in the appropriate mean and standard deviation. So the first one was I should have these numbers memorized. I've used them so long, I've already forgotten it. 5910. Just leave it as left. I would always leave it as left. We're not going to try anything too creative on these. So once again, if you're using the 83 like you saw on my notes there, all you need is the 5910, and that's it. If you're using this calculator, I mean, just leave that stuff there. There's no point in deleting it, but just leave it there. In fact, for the other one, I'm going to do it as if, I was doing it for either kind of calculator. But technically, I could put 9616 and change it to right tail down here. But let's just do it as 1. Let's just treat it as left by going 19616. And that way I'm doing it exactly the same way. In other words, I'm converting it from right to left by doing 1 minus. And there's the negative 1.77. All right. So you don't need the chart to do this. You can just do it with that. But the chart's not that bad. But I'll mention the chart kind of as we go also. But you can kind of ignore that. If you want to talk about the chart, you can pretty much ignore it. Okay. Yeah, this is what we're interested in, is finding, percentiles, scores. So let's say you know, you took some, it could be like a standardized exam, whatever, standardized test. And let's say, you know, they give you the percentile. But let's just say hypothetically, if you knew the mean and standard deviation and you knew your score and you knew that they were normally distributed, you could figure out what your percentile is. Pretty straightforward. Now, let's talk about how to get these z-scores that, you know, sometimes on the test I might just ask, okay, what's the z-score? And that's what we've kind of been doing. But keep in mind now, percentile, we don't have to worry about left, right. Remember the definition, percentile always means the percentage of scores that are lower than that value, whether we're talking continuous or discrete. So that always means left. So there is no interpretation of left or right here. It's always left if it's worded as a percentile. Now, the example I had on the last page was not a percentile. It just said area to the right. That's different. Percentile, always to the left. So nothing fancy there. Now, so this subscript notation is for percentile. So like P35 is 35th percentile. So suppose we want to find the z-score that corresponds to each percentile, like 38. So I kind of drew a picture. Now here's where we're going to get to where they don't often hit the chart exactly, which isn't a concern if you're using a calculator. But if you're using the chart, what you want to do is if you want to pick the closest one. And if it lands right in the middle of two, I guess you could just pick either one of them. Some of them are right in the middle. So like this one, I'll skip. But anyway, I just kind of pinpointed the two numbers. What I always do if I'm using a chart, I would pick, you want to pick the closest one to it. So between these two numbers, 3821 and 3783, 0.38 is actually a little closer to 3783 than it is to 3821. All right, so then I would pick this one, and that's it. You can't see it there, but that's the first column's 0.00, that's 0.01, so it would be negative 0.31. We'll do these in the calculator here in a second. So next one for 72nd percentile, the z-value is you kind of pinpoint, if you're using a chart, where it's between. Always identify where it fits. It fits between these two numbers, then identify which one is it closer to. Yeah, all we care is closest to. It can be the one that's greater than or less than, but whatever's closest. So I do believe that 0.72 is going to be a little closer to 7190 than it is to 7224. So I would pick 0.58 because it's in the 0.5 row, 0.08 column. And here's the calculator screens, but I'll do them real quick because it doesn't take that long to do them. So let's go second. Distribution, inverse norm, 0.38. There's negative 0.31. And the other one was what, 72 or 70? 72. So change that to 72. .58. So you just round these to two decimal places. All right. So I don't think that's too bad. And there they are right there on the notes. Now, transforming a z-score to an X value. Like I was saying, X value would mean in the sense of, like I said, if you wanted to find what would have been your test score, you know, based on a percentile and a mean and a standard deviation. So we'll be given the mean and standard deviation in these problems, and then they'll give you the percentile level, which means theoretically all we have to do is convert it to a Z, and then we can calculate the X, the value that would transform, you know, what would that value be that corresponds to that particular percentile. And all this formula right here is, and this, whatever this kind of maroon looking color is, it's your regular z-score formula right here, algebraically rearranged to where it's just solving for x. That's all. So, we don't have to do that every time. It's already just solved for you. Yeah, so it's just an algebraic rearrangement of this formula up here. Okay, let's look at, these aren't percentile questions, but these are easy. So here, see, it says normally distributed, gives you a mean of 67, standard deviation of 4 miles per hour. Find the speeds, x, corresponding to the z-scores of 1.96, negative 2.33, and 0. Okay, so this is even easier if they just give you the z-score. You just put it right in the formula because you got everything you need. Mu plus z sigma. So remember, these z-scores, they translate to the number of standard deviations that you're above or below the mean. So for the first one, you take the mean, which is 67, plus the 1.96 z-score times the standard deviation, which is 4. So if you're traveling about 74.84 miles per hour, you're 1.96 standard deviations above the mean. The next one, negative 2.33. So all you're doing, same formula, you're just replacing the z and making it negative 2.33. And that gives you a value of 57.68 miles per hour. So if you're 2.33 standard deviations below the mean, I highly recommend you staying in the right lane of the road so you don't get run over. But anyway, the next one, 0. So yeah, the z is 0. That means the value will be the mean itself. And the formula dictates that because 0 times anything will be 0. So if the z-score is 0, that person is traveling the mean speed, which is 67 miles per hour. All right, isn't that pretty exciting? I can tell. I can feel your excitement through the air. I got this data from some other book somewhere, and they probably reference where they got it from. I probably should include it, but sometimes I'll admit if I just make up stuff, but this one, I got it from somewhere. I don't know how they collected it, but I didn't make that up. Survey, men 20 to 29, mean height was 69.6 inches with a standard deviation of 3 inches. Assume the data is normally distributed. What height represents the 80th percentile? In other words, that would make you roughly taller than 80% of the males in that group. All right. Now, if you are choosing a formula method to do this instead of calculator, that's fine. But what you need is you need that z. See, the last problem with the roadway speeds, they gave us the z. But here's a more typical type of problem that you would have on an exam, which is now exam 3, not exam 2. You got to get the z from the percentile. So if we're doing it this way, that's not hard because you have the mean and standard deviation. You just need that one number, the z. And I just have the chart snippet right here. So if you're doing the chart way, you'd go in and find the closest one to 0.8. And you see the one I saw. So I'm indicating the 0.8 is between 7995 and 8023. But it's closer to 7995. So I picked that one. So that's in the 0.8 row. 0.04 column. That gives me a z-score of 0.84. And then, I'll mention you don't need the left part here. So let's see. Yeah, let me show you this way, then I'll go back and put it in the calculator and show you that way to do it. So here you just got the 0.84. We already have the 69.6 and the 3. Those are given. So 69.6 plus 0.84 times 3 is 72.12. So if you're like a smidge over 6 feet tall, I mean, just a smidge, not very much, you should theoretically be taller than 80% of the men in that age group. So that's if you're doing it this way. We can do this thing straight in the calculator. We do inverse norm. Now this time we're gonna do the whole problem in one step here. We can do it all in one step. So if I put in 0.80 right here, and then if I go down here and hit paste, it's going to give me that 0.84. It's just going to give me the z value. But if I put the mean and standard deviation in right here, I'll get the direct answer for x in one step. Now, of course, keep in mind if you do it this way, which is I'd recommend doing it this way, but if you're doing it, then you go back and you do some problem where it's only asking for the z value, you'd have to go back and make sure you change those to 0 and 1. You know, let's say if it says find the z value that corresponds with the 43rd percentile, then you've got to make those 0 and 1. But if you're finding the x value like we are here, we can do it all in one step. $72.12. Which was our answer. Now, keep in mind, this happened last week as I talked about, you know, the preciseness of the calculator versus, you know, when we're just using rounded answers. Most of the time, these problems in these test banks, they're using answers that are based on if you were using the chart. Now, this one happens to be pretty close, but I guess my point being is other problems, it might be a little bit off. And I think that the homework is going to be okay, I believe. On a test, I would just make sure the answers aren't that close together. So you would just, let's say, for example, let's say the calculator was 72.16 or 72.17, and you saw 72.12 as an answer choice, and you know you did it right, pick 72.12. There won't be a 72.17 to choose from. A lot has to do is how close does your percentile fit to your number here? You know, see, 0.8 is pretty close to 7995. So it's going to be a pretty good match. If it fits more in between the two numbers, the final answer will be they'll be a little bit off from each other. Technically, you can make the case that the calculator answer is more precise, but it's because we're only using 2 decimals for the z when we use the chart, so it makes it a little bit different. But I think the homework should be okay. Hopefully, I believe that's we'll see what happens. I hope that's not an issue in the homework, but it will not be on the exam. That you just have to just be confident to pick a pretty close answer to that. And just know that, oh, okay, this was done using the chart. That's why it's off. And no need to panic. Let me come up here and look at part B. Now, part B is kind of interesting. It says, what height represents the first quartile? And you might think back to how we handled quartiles back in the day. You know, where you broke median, then we broke each half into each half, found the quartiles, and the TI could actually do the quartiles by listing the data. But that was for discrete data. That would not work here. So what we have to do here is we can't do it that way. What we have to do here is just translate first quartile into what it actually means, which is the 25th percentile. So you just treat it as it's the same thing as if the question was asking the 25th percentile. So that's a little sneaky because you might have been, hey, where's my data? How am I going to break this down? No problem. It's just the 25th percentile. Now this one, so here it is. If you're using the chart, like I said, I'm kind of skipping past that real quick, but 0.25, 25th percentile. It's closer to 2514 than it is 2483. Negative 0.67. And all right, so if you did it that way, you would just put in negative 0.67. You have the same mean, you have the same standard deviation, and you would get 67.9. So we would say we would expect about 25% of the males to have a height of less than 67.59 inches. In the calculator, you know what, I could probably just go second, enter, like last command. Yeah, I mean, you can just redo it from scratch. I can just go back and type right over the 80. Since we're using the same mean and standard deviation. But whatever, if you want to go, do it the other way, that's fine. Okay, this one's not too far off, 67.58, but still a little bit off, not much. All right. Very good. All right, suppose old Getty Lee took an accounting exam and we were told that the score was, okay, you're in the 90th percentile, Getty. The exam scores are normally distributed with mean 72 and standard deviation 12. What was Getty's score? We'll say rounded to 1 decimal place. Okay. So that's what I was saying earlier about how you could, if you knew the percentile and you had this other information, you can, and assuming normally distributed, you could figure out what the actual score was, and that's what we're doing right here. So we have the, we go to, if we're doing the chart way, the closest one to 0.9 would be 8997, and that's 1.20, 1.08 column. So the Z, there it is, the P90, the 90th percentile is 1.28. So you plug it right into the formula. And 87.36. Oh, I forgot to mention in the last problem, if you're using an 83, yeah, you can do the same thing in the 83 for this one. I have it right there though for that problem, but not for this one. Wait, no, I didn't do it for this problem. Let me see, is it? No. In the 83, you just don't need the word left there, but you got to put 0.8, comma, 69.6, comma, 3, and close the parentheses. It doesn't need the word left there. See, if you don't put anything after the 0.8, it thinks you want the Z value only. But you got to put the mean and standard deviation. In other words, the 83 it's defaulted at 0 and 1. Well, they're all defaulted at 0 and 1, but you have to type them in there. So same thing here. You would 83. You would put everything in there but the word left. And you see, so here's how to do it for this problem. It's 0.9, 72, comma 12. That's all you need. This one already has the left in it, so there's no point in getting rid of it. But we're going to be doing ones out of homework, so I'm not going to redo this one in the calculator. But I think you can see how to do it by now. If you're using the fancy one. Okay, wording is a little tricky on this one, but I like the challenge of thinking about this one. It's not super bad. All right. Okay. Annual cap, yeah, I got this one somewhere too. Capital consumption of ice cream in pounds. Normal distribution with a mean 15.4 and standard deviation 2.5. Yeah, this one you probably wouldn't be necessarily as proud if you were in the higher percentile for this one, but no well. So what is the smallest amount of per capita that will put, what's the smallest amount that can put you in the top 25% of the consumptions? Meaning, what number puts you on the mark where 25% of those values are above you, more than yours? All right. So what we need to do is we need to convert that phrasing into what it means as a percentile. So if 25% are above your number, that means 75% are below that number. So long story short, this graph down here shows you it's the same thing as this asking you the 75th percentile. So the smallest of the top 25 makes you above 75% or below you. Okay. Yeah, so any kind of wording like that, so if it says, okay, whatever, some medical school is going to accept 2%, I don't know, I'm just making this up, of applicants, top 2%. That means it would be the 98th percentile. You have to be at least the 98th percentile or higher. Okay. All right. Maybe over to the right, I have the picture if you're using the chart. $7.5 is a little closer to 7.486 than 7.517. So 0.67 would be a good choice here. And then if you plug it in the formula, it'd be 15.4, 0.67 is your Z, 2.5 is your standard deviation, 17.075. I'll put this one in the calculator. Yeah, this one's going to be a little off here. So it's 0.75 below. I already forgot these numbers. 15 point something and 15.4 and 2.5. Just let that stay left all the time. All right, a little bit off, but nothing was done wrong. It's just the rounding of that Z, and then because this 7.5 falls pretty close almost in the middle between these two. That's what makes it off. If it's closer to one number or the other, it'll match up better. But so on a test, you might see 17.075. Pick that answer because it'll by far be the closest one to what the calculator gets. And the next one, what is the largest amount that puts you in the bottom 15%? So it's the largest, that means 15% are below you. So whenever it's worded like this in part B, that wording is the percentile. So when part A, when it says the top percent, you go 100 minus that, but it gives you the bottom amount, that is the percentile. So bottom 15% means you are the 15th percentile. That means 15% are below you. And so there's 0.5, fits right in there, a little closer to the one I circled. So negative 1.04 if you're doing it with the formula. Pretty easy, 12.8. And that's a pretty good answer for this one too. 0.15, 15.4, 2.5. So the 83, you would just cut it off right there at the 2.5, 12.8. There it is. Like I said, we're going to be doing these in homework here in a minute. Bags of baby carrots. Normally distributed with a mean of 32 ounces, standard deviation of 0.36 ounces. Bags in the upper 4% are too heavy and need to be repackaged. What is the most that a bag of carrots can weigh and need not be repackaged? All right, suppose you're down there, you're the floor manager of this operation. Yeah, weight I guess could be a consideration depending on the packaging materials, but I think another way you can actually look at this problem is well, you don't have to do anything to solve it, but I mean just from a business standpoint, I would think anything that you don't want to give away too many carrots. I don't know. It's just my theory. Anything upper 4%, we're giving away too many carrots. So evidently, maybe they got some sort of machine that, kicks it off the line. I've never been on an actual assembly line, but knocks it off, and then somebody could take that package and go back and open it up with the other carrots and goes through the process again. I don't know. I'm just imagining what it must do, but so mainly, you know, or it could be the packaging could potentially burst or something, but that's not much of a weight difference, really. See, the standard deviation is really low, so that's good. So your process is pretty consistent. So you're not giving one person 22 ounces of carrots and the next one 42 ounces of carrots. But, you know, we don't want to give too many extra freebies for business there, do we? But anyway, upper 4% means it's the same thing as 100 minus that. Upper and top obviously mean the same thing. So we want to find the 96th percentile. So we don't want the weight limit is whatever the 96th percentile is. Anything higher than that we consider too heavy. Now I just kind of hand wrote the chart here. 0.9599 is really close, and it turns out to be 1.75, but obviously if you're doing the calculator, you don't need to do it that way. But here it is using the formula, 32, 1.75, 0.36. Because yeah, when you're doing this in the calculator, you never actually see that p-value there. But know how to get that p-value, because that can be, you know, as we started out this section, that might be its own question on a test. So like that's what I was saying earlier about you would need to make sure it showed 0 and 1 for the mean and standard deviation. So you would just put in 0.96 and then 32 for the mean, 0.36 for the standard deviation. And there it is. You should get 32.63. All right, I'm just going to do this one in the calculator. I already have it done in the calculator, but I could use the chart. I mean, if somebody really clamors for me using the chart, I will, but if not, I can kind of bypass it and just do it in the calculator. Average, 49 minutes social media, standard deviation 16, normally distributed. What is the minimum amount of time spent to be in the top 10%? So the minimum of the top 10% makes you the 90th percentile. Okay. So the calculator is pretty straightforward. Second. Um, 0.9, 49, 16, 69.5. Okay. So that's what I was talking about, 69.48. That's probably what it is if you use the chart. It's just a little bit, but it's not, see, you see it didn't, that's the way I would design an exam question, the same way as this. I mean, look at the answers. There's no way you just pick the closest one and there's no way you can get tripped up. I think the answer, I could be wrong. No, I've checked before. I believe it's answer C, answer C, is if you did this as the 10th percentile. So that's different. That's different than rounding. That means you did it incorrectly. But I'm talking about I wouldn't want anybody to miss it because of these rounding issues. But I think answer C is if you did not correctly convert that to 90th percentile. You could try that real quick in your calculator, change it to 0.10 and see if that's right. See if it produces answer C. Yeah, that's not a rounding issue. I think this problem actually, I would never put this on a test, but I think there might be something like this on one of the homework questions if I remember correctly. So that's why I'll look at this just for a minute here. Maybe it's not this sophisticated. This is an interesting problem. Like I said, it's not worth putting on a test, but a lot of times that people that the expression of what people think curving grades means, almost everyone doesn't really understand what that means, and that's okay. That's all right, because it's not what you think it is. what most people think curving is actually just adjusting the grades. This is an example of what curving grades actually means. It's modeling them off the curve for the normal distribution. Just as the instructor said, okay, I'm adding 5 points to every test or something like that, or this test. That's an adjustment, but most people call that a curve. This is a curve here. This one's a kind of a rough one right here. This is not one. Now, this is the kind of situation I could see being used in maybe something like a medical school thing or engineering. Or I know engineering schools probably still do this. I know they used to do it, but they just not, a lot of their exams are designed to have like really low scores. And your grade actually is based on how you do against the competition more than just what your score is. You might take a test where, make a 58, and that might be a B, might even be an A. So it's kind of a little different than what you think. All right, so this says that, notice that it's showing that the top 10% of the scores are only the top 10% are making an A. Then the next 10%, next 20% are a B. The middle 40% are a C. And then the next 20 are D, and the bottom 10% are Fs. Yeah, this is a pretty tough one here. That's a little rough one. A lot of C's. I could see maybe 20, 20, 20, 20, 20 might be better, but this is so actually your score. So this one was this mean of 72 and standard deviation of 9. So to be in the top 10%, you'd have to be the 90th percentile. So I'll put P90 there, and there's the mean standard deviation. That means you got to be 90% have to be below you. And then here's the calculation. So an 83.5 would be an actual A on that test. Next one. So to be the B, you've got the bottom of the B's. Now we're always saying the middle. Obviously the B is going to go from the bottom of the B to the bottom of the A. That's the entire B range. But you see the bottom of the B has 30% above it. So to reach the minimum B, you have to be the 70th percentile. So it's P70. The minimum C grade means 30% or below you. So that's the 30th percentile. And then to reach the D level, 10% or below you. So here are the scores. So to reach the B, you got to have a 76.7. And then a C is going to be 67.3. And then a D is going to be 60.4, whatever. So that's just kind of interesting to look at that, because that's technically what curving really means, although I don't think you're ever going to run across that anywhere, most likely. I don't think anybody would grade this way. I'd be shocked if anyone really used this. Anyway, all right, that takes care of this. So let's jump over to the homework before we go on break here. All right, did it log me out? No, I guess not. Okay. Didn't know if I was gone too long. It's just slow. Nope, that's not what I meant. Okay, now this, you may recall from last week. If you don't, that's okay. But this is the one where all parts of the homework, even this part 3 is still part of that other homework. So what you can do, it's up to you if you want to. Remember, this stuff's not going to be on exam 2, so you could actually leave those parts as incomplete. That's what I mentioned last week if you were practicing, and you can still do that if you wanted to. But or if you just say, now I know how to do this, I'll just finish it, each question or whatever. It's up to you. Some of these are trickier on the homework than they ever would be on an exam. I remember one of these being a little weird. Maybe I don't know. Maybe it's not there anymore. But okay, just get past these and. Now, what I mentioned last week, if you want me to, it's up to you. I can, just for practice, I can run through this problem and do all the parts, you know. Or I remember mentioning last week that if I just clicked on the show completed problem, I can just get to that last part and get it correct. Maybe I'll work one of them, all the parts, and then for the other ones, just do the percentile ones only, in other words. Let me look and see. I hate to do the same ones. I don't remember. The truck one, I remember doing the truck one. I might not have done the bottle. I don't think I did this one, this exam score one, which that'll kind of tie in what I just got through showing you. This might be a good one to do the entire problem. But first, let me go back to the bottled water deal here. Or I could do the trucking one here, because I know that that's going to have a percentile in there that we didn't answer. Actually, let me look at that. Let me see how many parts are on this one right here. Yeah, we'll do this one. And then maybe I'll just do the percentiles on the other ones. Like this one. Well, I'll read the question, then I'll bring it up. Part D, 90% consume less than how many gallons of bottled water? All right, 90% less, that's 90th percentile. So all we got to do is 90th percentile. I'll tell you what, I'll do the problem first, then I'll look at the answer. We're not going to be able to get the check mark, obviously, but we'll see the right answer, so that's good enough. The mean is 34.4. Standard deviation is 12. I'll just do it this way. .9, that was it. 34.4 and 12. Let's look. So 49 point. Let's see. Oh, it changed it. I should have done. Okay, what was I thinking? Okay, well, I can redo it, but I'm pretty sure that one was right for the one I did, but it's too late to check. Oh, yeah, I should have done this first. Well, I can change it real quick. It's 30.3, it's 12, and now it's 99.5. Sorry about that. So 0.995 for 99.5. I already forgot. 30.3 and 12. Okay, that one turned out right on the money pretty much. 6121. 6121. Yes, you see, that wasn't difficult. It's just that we didn't learn that last week. So let's do the truck. Looks like they've got couple of percentile questions here. Part C. How many miles traveled by at least 70% of the trucks? You got to be careful when you think through this. We haven't had this wording yet or whatever, but it could be easy to interpret this, but not if you just realize that at least means greater than or equal to. So that means we need the percentage below that. Sometimes I've had people in the past sort of misinterpret this, and I can see how, but that's the same thing as the 30th percentile. Because at least 70% means 70% or more than that, which means 30 would be less. So it's 30th percentile. All right. So what are we looking at here? $70,000 miles and 12,000 miles. Yeah, I remember when I did these earlier last week. I think I just used these numbers. I told you not to worry about putting them in thousands. I don't think we needed to for these parts, but we're going to need to for this, because you see we got to come up with a thousands of an answer there or whatever. So I will need to here. 70 and 12 and 30%. Point 3. And 12,000. So there it is, 63707. All right, now there's another percentage one down here, percentile. Okay, this one changes the standard deviation. Oh, okay, it's the same question. You're just changing the standard deviation. Okay, so it still says at least 70. Standard deviation is 9. All right, so we can just make a real quick change here. Well, 9,000, obviously. I can either retype them all or just go second enter and type back over it like this. I'll put a 9, then I'll hit the delete key to get rid of the 2. All right, looks like I got it. 65280. Look at us. We're too cool here, aren't we? We're kicking some percentile butt here. All right, now I'll release this one because we'll just work all the, okay. This will take us back to last week. So now this is a normal probability. Below, less than, mean 74, standard deviation 9. So kind of a refresher to last week. And when it's less than, okay, that one's already defaulted there, but that's where we need, that's what we need. We need that to be, that's your negative infinity. Less than always starts at your negative infinity. And I've already forgotten the number here. 90, 74, and 9. So negative infinity to 90, 74, and 9. Nine, 6, 2, 3. All right, let's see what that does for us. Tremendous. Between 65 and 93. I could actually do a second enter here if I wanted to. Lower 65. Delete, delete. Three deletes. Oh, crap. I already forgot if it's 83 or 93. 93. Eight, 2, 4, 0. Nice work. I just want to mention before we move on, that did two of the three cases, but what if it would have been greater than something? Let me do that real quick. I'll just make up one. It's not one of the questions, but you got to do the orders. So let's say if it was greater than 80. Just a quick reminder. You would start, when it's greater than, you start with your number, and then you do the positive 1e to the 99. That's your positive infinity. So when it's less than, your negative infinity goes first. When it's greater than, you finish with positive infinity. So we obviously, we're not 2525. We're not typing that in or anything. But just want to remind you the basic setup for greater than. All righty. Nope, wrong ones. The probability is worded a little tricky here. The probability is 25% that a student takes the test scores higher than what grade? Yeah, I don't think I'd use this kind of wording on a test. But we're gonna reason through this here. 25% of the student scores higher than what grade? So only 25% of the students are going to score higher than that specific grade. So that means that 25% is on the upper end of the graph. So this should be a 75th percentile question, meaning that 75% are going to be below that score, because that gives you a 25% chance that it's higher than that score. Hopefully that reasoning made sense a little bit there. I believe it's 75%. I got to be careful because I've misread these things before too. Hopefully I didn't this time. I'm going to go with 75%. Okay. So 0.75. 74, I believe, is the mean. I believe 9 is the standard deviation. 80.07. Nearest integer. Okay. So I'll put 80 in there and see what happens. Tremendous. All right, now you know how to do that one perfectly. Okay, professor grades on the curve, like I was talking about in the note. That's why I was glad I kept that in the notes, because it does come up here. It's exactly like the one I did there, to 10% of the A's. Is a student better off with a grade of 92, means 74, standard deviation is 9? All right, let's kind of go through this carefully. Yeah, these curve things could really be rough if it was a easy, pretty high grades. Because it might be like 98 or higher as an A and 96 as a B, or some weird, bizarre stuff like that. Because if the scores were high, that'd really be. I can't imagine anyone using a curve. It's only usually curved for low scores. If somebody wants to intentionally have harder exams, and then students' grades being based on how they do against the competition. 92. All right, so 67 mean 63, standard deviation 4. So, oh, they're using an example of top 10%. Actually, okay, it's not a percentile question. It's just a z-score question. So this kind of goes back to that question I had on the first exam, better relative position. Okay, this isn't a percentile question. This is where you just calculate the two z-scores. So 92, 74, and 9. It's pretty clear that that's going to be the best one. And the other one is 67 score means 63, lower standard deviation. But not enough to make 67 a good score, really. But. So the 92 is better because it has a higher z-score. And the higher z-score is going to naturally be a better ranking, which is going to make it better. So, all right, let's figure out how to answer this. The student is better off with the 92 because the z-value for the grade of 92 is 2. I guess if I would have read this question carefully here, I would have seen they were just asking for the z-score. And that z-score is just 1. Oh, it says round to 2 decimal places. I probably don't need to because they're exact values, but that would be funny if I was wrong here. But I mean, you could put 2.00 and you could put 1.00. But if they were obviously like 2.33, if different numbers produced, then you need to do that. But since those were exact, I'm hoping it's okay. Got it. And I'll go straight to the percentile on this one too. Country A. It's kind of a weird question. I was reading this question and you expect something that has it labeled as a country A. You might be expecting a country B. Why does it need an A if there's no B? Okay, never mind. Yeah, we've had problems before doing other stuff with 2 different data sets. And yeah, that implied to me there were going to be 2 different data sets. Well, that's okay. Never. So, okay, it's asking 97% consume less than. Okay, so that's straight up percentile right there. That'll be the 97th. Oh, well, crud. Let me undo this. It'll now be different whenever I release this. Oh, crud. Well, let me just do that just so we can go on break here. Let me just leave those numbers there and just do that problem. Mean is 18.96. Standard deviation is 4. And it's the 97th percentile. Let's see how we did here. 26.48. Yep, we got it. Beautiful. All right, break time. Is our usual 10-minute or so sufficient enough? Or 12 minutes, 10 minutes. I got 8:13. I don't know. 8:25. Is that all right?
Sure, that works.
All right, thank you, sir. 8:25 it is. Okay, we'll see you in a little bit. Welcome back to the show. Please, no applause. All right, let's see what we got here. Let's get some new notes. And I guess can go ahead and open up the new homework, even though we don't need it. All right. Sampling distributions and the central limit theorem. All right, let's see what we got here. Sampling distribution is a probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. We are interested in the sampling distribution of the sample mean, x bar. Lots of versions of the word sample in that paragraph. But sample distributions can be done for a variety of other things too, but we're interested in just the sample mean and how it's going to relate to this thing called the central limit theorem, which the central limit theorem is a very, very important and useful theorem in statistics. And let's talk about what that's all about. And let's say it describes the relationship between the sampling distribution of sample means and the population that the samples are taken from. Let's talk about, let me come down here. I might come back up here. Well, I'll probably jump around a little bit here. Might go down here to the graphs, then come back up here. What the central limit theorem is essentially doing now, in other words, let's say you had let's say you had some data distribution X. Yeah. Maybe it looks something like, this, whatever, something like that. Whatever the case may be, definitely not the normal distribution. Now, when we say distribution of sampling means, what we're doing is you're creating a whole new data set from that original data by taking samples of a specific size, whatever, 10, 50, or 100. Let's say if n was, you're taking samples of size 10 or something. And we're not going to be doing all the mechanics of this, but if you took the entire population, and let's say you took 10 numbers out of that population, you calculated their sample average, that gives you a sample mean value. Do another 10, gives you another. Another 10 gives you another, so forth, so on, blah, 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 blah. Now, we are going to be maybe interested in what that particular graph is going to look like. In other words, if just those values for x bar are plotted. Now let's go back to the central limit theorem and see what how that can be useful for us. Okay. And the first definition is the key to this. Is if the sample sizes are at least 30 or more, and the larger the better, but 30's the standard cutoff number. If you're drawn from any population, so as it says any, it doesn't have to be a normal population. It could be like that little mountain range I just drew on the other page. And you have its mean, you have its standard deviation, and then you plot those x1 bar, x2 bar, like I was showing you, it's going to approximate a normal distribution. In other words, doesn't mean it'll be a perfect normal distribution, but it will be close enough to where we can treat it as a normal distribution and we can find probabilities and stuff like that. Now here saying the greater the sample size, the better. Now part 2 just says if your data is already normally distributed, it doesn't really matter what the sample size n is. In other words, if x is normally distributed, x bar is automatically normally distributed. So let's say, let me come down here to to this picture here. And let me change, I should have put something bigger than 30 anyway. Let's say that was 40 instead of, and this coming from that data right there of x's. That means if x bar was plotted, now I'm not going to draw a perfect normal, I'm just going to draw kind of a, a little bit erratic looking one, but just kind of give you the idea. It's going to be close enough to a normal distribution that we can work with it. That's the whole idea. The larger the n, the actual smoother the graph that would look. But and if that's a normal distribution, we're in business. So what this means is if we have a data set that's not normally distributed, and if we decide that we're going to work with x bar, and as long as n is 30 or more, we can find probability values for x bar instead of x itself, meaning instead of saying if we take, we have a, I don't know, SAT math score from a mean and a certain standard deviation, and maybe it's not normally distributed. So, and we want to say, what's to find the probability that a score selected at random was greater than 650. If it's not normally distributed, there's really nothing we can do about it. We can't use normal distribution techniques. But let's say if the question was rephrased where, let's say if we took 40 scores, average those 40, what's the probability that the average of those 40 would be greater than or less than or whatever your number of interests there or whatever. You could then do that because the sample size being 40 means your x bar is going to be approximately and normally distributed. So let me go back up here and show you these pictures I cut out from somewhere else, which will be similar to what I had I just drew basically. I'll come back to these two things right here, which are very important. So let's look at the first case right here, case number 1. This is just notice I can't call that a normal distribution because it's kind of an erratic looking mountain range there, isn't it? But obviously any data set's going to have a mean and a standard deviation. Who knows how they determine all that business there. The mean's not necessarily going to be right in the middle of this either, like it is for a normal distribution. Obviously, depending on how skewed it is. But this says, hey, if you take that same data set and if n's greater than or equal to 30, it's hard to read. This is very faint there on the x-axis. Let me write that in there. But they're showing you that your original data set's always x. But now x bar will plot out to be normally distributed. That's what we're saying. Now, let me come up to this part, which is very important right here. When we're doing normal probabilities, especially the standard deviation, that's the key. The mean's not a problem. Anytime that you are given a mean and a standard deviation in a problem, that is always for the original data set X. So in other words, we didn't use these, you probably won't see these written anywhere or whatever, but I wrote them in. When we say mu and sigma, that's for x. That's because we weren't doing x bar yet. Well, this is telling me that the population mean of all those sample means is the same thing as the mean as the original data. So that'll work out to be the same number. In other words, the mean of the mean of the mean equals the mean. It's kind of confusing. So let's say if I took, if we calculated the mean for this entire data set, and then we did this business right here where you calculated every one of those sample means, and then you averaged all those sample means, the average of those sample means would be the same as the mean of the original data. So nothing changes there. But the key to all this, and making sure we don't mess this up, is the standard deviation. The standard deviation for x bar will be the given standard deviation divided by the square root of n. N will obviously be given to you. So will the standard deviation. So you're going to have to always remember to take, even in the calculator, you're going to have to remember to do that. Or use a normal CDF. You're going to have to remember to do the standard deviation, then divide it by the square root of n to get your new standard deviation. That's going to be the key to all this to make sure we get our normal probabilities correct. And other than that, one little numerical step right there, everything we do is going to be the same as we did before. I'm not doing percentiles with this stuff, but I could, but I'm not. We're just going to do regular normal probabilities. Oh, let me show you what normal, the number 2 is just showing you. This is just showing you if your original data was normally distributed. The new data for x bar is still going to be normally distributed. Notice it got a little thinner. The reason for that is, we talked about that last week. When you take this, well, not this part we didn't talk about, but when you take the standard deviation and you divide it by the square root of n, that makes it a smaller number. Remember we learned last week, the smaller the standard deviation, the skinnier the graph is. Yeah, we learned that last week. So that's why it got a little bit skinnier there, but it's still normally distributed. But the one on the left, though, you got to take it, n has to be at least 30 for the sample means for it to turn into a normal distribution. Anything less than 30 for that one would be no good. But if it's already normally distributed, n could be 10, 5, whatever. It wouldn't matter. Now, this is very important. I usually put one of these on a test. If you don't fall into the trap here, it's easy. If you pay careful attention, it's easy. If not, you could make a mistake. Alrighty, annual snowfall has a mean of 100 inches and a standard deviation of 14 inches. Suppose snowfalls sampled during randomly picked years for samples of size 49. Determine the mean and standard deviation of x bar, of the sample mean. Very important. Because like I said earlier, the mean and standard deviation numbers that are given to you in the problem are always going to be based on x. They want x bar. So here's the catch, where you be careful not to fall into the trap, because it looks like D would be the right answer. Because you see, no, sorry, not D, B, excuse me. I got them backwards. Even another way to mess it up. But no, because it says, hey, there's a mean of 100. There's a standard deviation of 14. I'm done. The answer is B. The answer is not B. That is the mean and standard deviation for X. The mean is correct at 100. But we have to take, see that 49, does come into play here. That's your N. That's your N is your sample size. So the mean's the same. So mu of X bar equals regular mu equals 100. but it's all about the standard deviation. Standard deviation of X bar is the original standard deviation divided by the square root of n. I guess I jumped ahead of myself here. That is the right number, but so it's not 14, it's 14 divided by square root of 49. Now they made these numbers work out nice and clean. You can probably assume they're going to be decimal type answers in the homework or test. Looks like they did this one on purpose. Square root of 49 is 7, so you didn't have to know that, obviously. But that's why A is the correct answer. The standard deviation of X bar is actually 2. So we don't want to fall into that trap. If we don't do that, we should have no problems. Everything else here is going to be exactly the same. Now, of course, the question will be, now, actually, it won't be much of a, well, I guess on the final, when everything is back into play. But since these are on 2 separate exams, I'm just going to pretend like you have to make the distinction between the two. You really don't, but I'll talk about, how do we know whether we're solving a problem, whether it's X bar or it's just for X? Yeah, exam 2, it's only going to be X. Exam 3, it's only going to be X bar, but the final can have both, which will have both. So look at the Z-score formula. Once again, if you're using the calculator, you'll be able to use the calculator. Still taking your mean, subtracting, the sample mean minus the given population mean. But notice, it's not just sigma on the bottom anymore. It's sigma divided by the square root of n. Now, how do we know when it's X bar versus X? A couple different ways. You're going to have a sample size in there. Everything, if you go back and look at everything we did last week, we were always choosing one thing. What's the probability that a utility bill is selected at random? Or the probability that Dodge Durango, I think was one of the problems. I don't know, got more than whatever miles per gallon. A means 1. We were only selecting one item. Here, you're going to have a sample size of more than 1, and then the wording of the question is going to say, find the probability that the mean, I like to do that for effect there or whatever, not the probability of that one item, probability of the mean, meaning the average of how many things there were, is either less than, greater than, or between 2 numbers. So everything's going to be the same. It's just the standard deviation. Now, I worked this out the long way, but I'll show you how to do this perfectly in the calculator. Okay, this says normally distributed amounts of coffee, so that means the sample size can be any number, it doesn't matter. It's only when it's when it's not normally distributed, the n will be at least 30. Mean is 12, standard deviation is 0.2. We're selecting a sample of 9 cups, okay? So right there, we're sampling more than one item. Find the probability that the mean of the sample will be greater than 12.1 ounces. In other words, if you took all the amounts from each of the 9 cups and averaged them, what's the probability that average of those 9 cups is greater than 12.1? Obviously, you're not taking those numbers and averaging them. I'm just explaining to you conceptually what's going on. Pretty exciting. So you see, so now I'm just using the variable X bar instead of X, greater than 12.1. So on the top, it's pretty much the same. It's 12.1. Your value you're calculating minus the given mean, which is 12. But look at the problem. The denominator is not just 0.2. It's 0.2 divided by the square root of 9. If you're doing it this way and you get 1.5 greater than, it means flip it and change the sign. But if you're using a calculator, you can just treat it as greater than. You don't have to flip anything. That's just if you're using the chart. We learned greater than means flip it. Well, there are two ways to do it, but I think that's the better way. Flip it, and you look up negative 1.5, and that gives you 0.668. Now watch how we do this in the calculator. Go second, normal CDF. I'm going to treat this as greater than. We're not going to worry about any flipping. Greater than means you start with your number, then you go to that 1E99, which represents the positive infinity. And I've already forgotten these numbers. Oh, that was 12. And then 0.2, and then 9. So 12. Watch what I do here. I don't have to calculate this in advance. I just put 0.2 divided by the square root of 9 right there all in one step. Yeah, you don't have to do it in advance, but you can if you want to. But you, at some point, and this is perfectly fine right here, you got to be dividing by the square root of 9 there. So that's all you got to do is just type that in there right there at that step. And there it is, 0.668. Ta-da! All right. And there it is, 0.668. Now then I changed the question to make it look like something from the earlier material. And we can do that because remember the original data was normally distributed. If it was not, I couldn't even make up. If I made up this question, it would be wrong for me to even make it up. In other words, it'd be wrong for me to even assume that I could say selecting one item. All right. Okay, so well, because it's normally distributed, we selected one. So this is going back to last week. So you see, and I'll put this in the calculator, the only difference is we don't divide by the square root of 9 on the bottom. It's just 0.2 on the bottom. Obviously, it gives you a different z, which gives you a different answer, but that's the only difference in the calculation. So in the normal CDF, I guess I could have typed right over. That's okay. I got to just come down here and just put in 0.2, and that's it. There is no dividing by the square root of 9. And that would have been how we would have had this question asked last week, because last week it was just only for X, one item. Isn't this fun? I'm pretty excited. So this is really all we do is plow through some examples. We're pretty much done. That's the only new. I'm just got to look at these examples. May not do every one of them. That way I can just jump to the homework. Oh, actually, I did do a percentile here. I added that in there. I forgot because there must be one in the homework. So I went ahead and did it. Probably won't put it on test, but it looks like I did put that in there. We'll talk about that problem. So I may not do every one of these. I may skip over some of them because we're going to see some, live action in the homework. Let's certainly do the first one. Oh, we just did the first one. Let's do the fishy. Normally distributed with 11 pounds, standard deviation of 6 pounds, obviously. 4 fish are randomly selected. Okay, we're selecting more than one, so that tells me we're, going to be doing the X bar. What is the probability that the mean will be between mean weight, the average weight of those 4 fish will be between 8.6 and 14.6? So if you're doing it the long way, You convert both ends to z's. 8.6 minus 11 over 6 divided by the square root of 4. That's the key. On the upper end, it's 14.6 minus 11 over 6 divided by square root of 4. You get two z values here. We learned last week that if you're doing it this way, you look up the two z values. You take the larger one minus the smaller one. You look them up. There you go. In the calculator, I'm not even going to type this one in. I'm just going to just mention it. So remember, when it's between two numbers, that's the only time you don't have either the negative 1e to the 99 or the positive 1e to the 99. You just put the two numbers, lower and upper. So you put in 8.4, you put in 14.6. The mean is the same as 11, but look at the standard deviation. You've got to put 6 divided by square root of 4. That's the key. Paste. 6, 7. So 6731, obviously you're not going to miss it on a test. I don't think you will on a homework either, but looks like this one was designed to match the chart answer, but obviously that answer is close enough. Okay. I always think I'm going to go back and change the wording of this problem one day, but I'll always forget because I always laugh when I see this. Rebuild the transmission of a 1992 Chevy Cavalier. No one's going to rebuild the transmission of a 1992 Chevy Cavalier. It'd be easier just to send it off the edge of the Grand Canyon. No, I'm just kidding, not that. But yeah, it's not exactly a classic car, but they were functional little vehicles back in the day. I never had one, but I knew people that did. Yeah, I just thought it was kind of funny. Yeah, not exactly a classic car you'd work on or anything like that. But anyway, average time is 8.4. Standard deviation is 1.8 hours. If 40 mechanics are randomly selected, find the probability that their mean rebuild time exceeds greater than 8.7 hours. Now notice this problem doesn't say anything about the normal distribution, nowhere in it. I believe the fish one should have somewhere here. Yeah, fish are normally distributed. This did not say anything about that. Okay, here's where the central limit theorem kicks in. Because our sample size is 30 or more, in this case 40, that means that the original data did not have to be normally distributed. We can treat X bar as if it is normally distributed. That's the key. Now, it could have said normally distributed. It didn't have to, so therefore I wrote it out right there. Since n is greater than or equal to 30, the sample mean is, should say normally distributed. That's poor English there. Now, of course, I'll probably forget to save and repost these. Distributed. Yeah. It's the normal distribution. So then, there you go. So if you do it this way, it's 8.7 minus 8.4 divided by 1.8 divided by the square root of 40 down there on the bottom. Greater than 1.05 would be the same as less than negative 1.05. 1469. So in the calculator, you don't need to do the flip-flopping. Just go ahead and treat it as a greater than. So start with greater than, start with 8.7. Use the 1E99 as your positive infinity. Use 8.4 as your mean. And then use 1.8 divided by the square root of 40 as your standard deviation. And there you go. A little bit off. 1.1459, but we're doing it correctly. 1469. You see nothing else is close to 1469, so we're good. We're okay. Okay, I might just skip this one. Nothing wrong with it, but just to kind of move on. It'll stay in there, so obviously you can look at it and certainly could ask me any questions if you have any questions on it. Or let's see. I'll look at number 6. Yeah, this won't be an issue for those of you using the calculator. I mentioned this briefly last week for someone using the chart. Okay, women's height 63.6, standard deviation 2.5, 75 women are randomly selected. Okay, this one does say it's normally distributed, but it didn't have to be normally distributed because the 75 is more than 30. So it didn't have to be normally distributed. Find the probability that the mean height is between 63 and 65. So we have to convert, if we're doing it this way, convert both ends to z's. So it'd be 63 minus 63.6 over 2.5 divided by the square root of 75. And then just change that to 65 over here. And you get negative 2.8 and you get 4.85. I mentioned this in the notes last week that if you go off the chart, say in the calculator, you're not going to have that problem, but because you don't have to even get these individual values. I always just say use like 0.9999, or you could even use 1, it would be okay. If it was off the chart in the low end, you could use 0 or 0.0001. But this isn't, for calculator people, this isn't going to be an issue. But I use 9999, and then the other one is on the chart, negative 2.08, and I got a pretty good match right there. So, okay. All right. So on the calculator, you would just put 63 lower, 65 upper, mean is 63.6, and then standard deviation is 2.5 divided by square root of 75. Paste, and there you are, right there in the correct ballpark, 9812, whatever. That's good enough. I'm sure the homework would accept that. All right, let's try the sweeter sugar problem. I thought this one, I usually keep this erased in the notes. Well, that's all right. I'm not going to erase it now. It's already there. So we've got plenty of fresh problems to do in the homework, so that's okay. Average weight of 16, standard deviation is 0.3. The weights of the bags are normally distributed, and that's important because we're only selecting 9 bags. I guess if it didn't say it was normally distributed, for our purposes, you would just have to assume that it was normally distributed. There wouldn't be any answers that said, like none of the above or something, because meaning you couldn't do it. I mean, I try to make sure it's worded properly on an exam, but in that case, you would just go ahead and assume it was. You'd have to be able to get the answer. Okay, what's the probability that the average of those 9 packages will be greater than 16.025? So 16.025 minus 16 divided by 0.3 over the square root of 9. And then all that mess will calculate into 0.25. If you're using the chart, you just flip it over and make it negative and look that number up. If you're using the calculator, it's easy. Just put in 16.025 as your lower. 1e to the 99 is your upper. The mean is 16. And standard deviation is 0.3 divided by square root of 9. In the problem above, there's a 30% chance that the sample mean of the packages is above what value? So I said earlier, I didn't think we were going to do percentages here, but percentiles here, but we are. So, okay, so 30% above that value means 70% or below. So that's another way of just getting the 70th percentile. But this is, like I said, not hard to do. it's the same formula, but it's all about this standard deviation. Just knowing that you got the divided by the square root of 9 there, that's the key. So if you do it the chart, 0.7 is closest to 6985. It's 0.52. So it'd be 16 plus 0.52 times 0.3 divided by square root of 9, which is 16.052. And the calculator, you would just do the same thing. You would use inverse norm, and use the right area, 0.7, there's the mean, and then you just, for the standard deviation, you just use 0.3 divided by square root of 9. So everything would work pretty much the same. It's all about that standard deviation. That's the key to all of this. All right, let's jump into the homework, see what we got here. Oh, continue just in time. All right. Okay, I'll kind of skip some of these preliminary ones. I think it's always more fun when there's like a little. I like they start out with those to give you just the practice of the mechanics of the problem. You know, once you can do the mechanics, then. Okay, let's see what we got here. Now we'll try this one. Tennis balls normally distributed. Mean of 2.52, standard deviation of 0.03. Random sample of 12 tennis balls are selected. Let's see, complete parts A through D. What is the sampling distribution of the mean? Now, because the original data is normally distributed, that guarantees the sampling mean will be that this will be normally distributed. Now, remember, if it was not normally distributed, the key here would be whether or not the sample size was 30 or more. So if it was not normally distributed and this was less than 30, you know, the sampling distribution could not be found. We would not know. But because the original is normal, we're covered regardless of the sample size. That looks like A. Let me just double check here. Should be it. All right, yeah. What is the probability that the sample mean is less than 2.5 inches? Okay. We can go right to the calculator for this. Do a little normal CDF. Less than means I'll start with the negative infinity. Yeah. 2.5. Look up here. Let's see. 2.5, 2.52. 5.2. Standard deviation is 0.03, but the sample size is 12, so it's 0.03 divided by the square root of 12. So you see how everything revolves around that? And I'm sure that's probably got to be the biggest frustration when somebody does mess one of these up, is because they forgot to divide by the square root of n. Okay. Okay. So rounded, that'd be 0.105. Nice work. between 2.51 and 2.53. Easy enough. I can type over this or I'll just go back in there. And so 2.51, 2.53. Is that right? Yeah. Seven, 5, 1, 8. Nice work again. This one is tricky. Not one that I would ask on an exam. Putting these in the middle. Now, I'm trying to think of just different ways to do it. Let me just explain one way. One way we can do it for sure. There's actually a way that, and I'll refer back to this later, but this in something we're going to be doing later in the next unit called confidence intervals next week. That'll work perfectly for this, but that's okay. I want to show you in case you want to do these. I'll show you this way, which won't be that bad by any means. So, but I need a picture to illustrate the effect here. We just have to do two inverse norms, but we have to know what percentages they are. So let me draw, it was 56 between the two numbers. So you can follow this exact process for whatever your percentage is or whatever. So we got 56 between there. Now I don't really need to know the upper end. I mean, it's going to be the same as the lower end, but I only need the lower end because, you know, we're working to the left here. Okay, so let's see how I can figure out what that lower end is. We know the whole thing is 100, correct? So the remaining amount, it's got to be 1 minus 0.56. It's 0.44. And since that's perfectly symmetrical, it's going to be half at each end. So how about if I put 0.22 right here? And it would be that way on the upper end. So we have to calculate now the area left of the lower, which will be 0.2, and then the area left of the upper. The upper will be 0.22 plus that 0.56 right there. So together, that's going to be 0.78. Does that make sense? Okay. Well, just, you don't have to say anything. Just if it doesn't, let me know. It's these two added together. That's going to be this upper mark right there. So long story short, then to get those two numbers, we can just do two inverse norms with one of them being 0.22 and one of them being 0.78, which if it gives you a new percentage, when you do it other than 56, you'll just have to figure out what those values are. So let me go back to the data here. Oh, it's the same data. It'll be inverse norm though, so it might not have it in there. 252.03. Since we're doing inverse norm, it probably won't have these numbers in there. Yeah. It only stores them if you're using the same command again. So I think it's 2.52. No, wait, yeah. And then 0.03 divided by square root of, is it 12? 12. Now this one we'll be able to do a second enter and just retype right over it, because it'll have the numbers already in there. I'll go ahead and just do that before I even write this down. I'll go second, enter. And all I can do is change 0.22 to 0.78. So let's see how many decimal places it wants. 2. 2.51, 2.53. Fantastic. Yes, I'm glad we picked that one, just so that one, I don't think they all have this, but that would have been tricky. Actually, I'll tell you what I'm going to do is before I decide the next one, I'm going to look at the components for all of them here, because if I see anything really, really weird. This one's not too weird. Now for this one, I'll mention real quick that you can go back and look earlier in the course of the definition of right skewed and left skewed. If your median is smaller than your mean, that is skewed right. So that's why this answer, probably going to be the same answer when you do it too. But that's the reason, is because that was defined. I wouldn't expect you to remember that off the top of your head, but that was back in somewhere earlier in the beginning of the semester. But that's the reason. I don't think it's going to change it. I'm not going to do that one. This one's got potential. Or either one of these. Oh, you know what? I forgot. I think it's in my notes, but I forgot to verbally say it. Oops. Well, it doesn't hurt anything, but I can go back and correct it now. Yeah, we haven't needed it yet, but yeah, I didn't mention this. I mean, you probably saw it when we were looking at it, but I was so focused on this dividing by the square root of n. That just happens to be called the standard error of the mean. So if it's asking you for the standard error, that is this calculation right here. Yeah, I just actually forgot to say that. I realize it now. So that's what's happening in part A of this problem. It's just standard deviation. But actually, though, it's showing you symbolically. So that's what it is. It's the standard, we already have that defined as the formula. The next one might have been a little trickier, because you see it just does it in words, the standard error, which means the standard deviation of the sample mean. Same thing. I think we can do this one. Maybe wrap it up with that one today. So it looks like that one problem was the only one that did the percentiles. Looks like for this particular section. I think we'll do this one with some fresh numbers and call it a day here. Well, I mean, I'm going to be available for questions and whatnot, but call it a day for lecture. So let's see. "90 students." That's not, I hate when they put stuff in there it's not necessary. The 90 is not necessary. The random sample of 39 is necessary. And that means the central limit theorem applies. So that, we're allowed to use the normal distribution. Well, like I said before, we weren't. We kind of wouldn't be able to do anything with it. But other than if the question said cannot be, or the answer said cannot be done. I would never do that on a test, but I don't know what's happening here. So standard error of the mean is standard deviation. Yeah, that 90. So ignore that 90. I was going to go 4.2 divided by square root of let's see how many decimal places it wants. 2. So 6725. So I'm going to go 0.67. Oh, no, not this business. No. No. We're not doing this. Dang. Well, that's all right. I'm going to do like I've done before. I'll just wipe this problem out. So let me go back and do the other one. So it's going to be mysteriously removed here. I'm not going to worry about that finite correction. So that 90 actually was needed. But we're not going to cover that. All right. Well, okay. So we'll just do this one then. And one less problem for you to do. All right. 38 theaters. 0.43 divided by square root of 38. Four decimal places. 0698 sounds good. Now we're in business. Less than 9.72. Normal CDF. All right, less than, it's already starting at negative infinity. So we're set there. And it's 9.72 with a mean of 9.59. And 0.43 and then 38. .43 and 38. So it's 0.43 divided by square root of 38. How about 9688? Nice work. Another less than. Well, heck, we'll make this one super quick. I'll just go second enter. I won't even worry about retyping everything in there. course, I just forgot the number, but I know it's 9 point something something. So I'll stop right there. 9.55. Easy peasy. Oh, huh. Got click happy there, didn't I? 2832. More than 9.68. So I'll put 9.68 here. More than will be 1. Oh. .68. I don't know what button I hit there. 1. Oh, I forgot to probably hit the second, and a comma came up, so it freaked out. And now I got to put the mean and standard deviation in there again, I guess, for some reason. 0.959. Ugh. 0.43, then divided by the square root of 38. Enter. 0985. Ta-da! So I think we're officially done. I'm going to get rid of this question. Go back, take care of that. I'm going to put this, save me some editing time here. I'm going to either stop the recording or at least put it on pause. If I can stop and still stay in the meeting here, I'm pretty sure. I'll just put it on pause and I'll stop it later. So I don't have to figure out, I always have to go back and figure out where to cut it off, you know. So I'll just put pause, and then you can ask and say, always delete the stuff at the end anyway.